Good afternoon, everyone. Very happy to welcome Ron Lavi from University of Bath. Ron has been involved in algorithmic game theory and specifically algorithmic mechanism design almost since the beginning, right, over 20 years. Worked with Noam Nissan, I guess, for your PhD. Yep. Right, postdoc at Stanford. Is that? At Caltech, that's right, that's right. And you see lately there's been, one thing that's really blown up over the last few years is contract theory, not so much contracts directly in the sense of smart contracts in the blockchain world, but in the sense of kind of microeconomics. And Ron's been doing some really nice work there. So he's going to tell us about contract theory, both in the traditional sense and also maybe connections to blockchain contracts. So, Ron.
The talk will be mostly based on a joint work with Elisheva Shamash from Technion. Since the early 2000s, we have seen many tight connections between economic theory and the new computational reality that has evolved so significantly in the past 2 decades. Most notably, we have seen these connections through auctions and auction theory. So it was a two-way connection, so it was not one thing influencing another, but actually it was like a relationship, one object influences the other. So the new computational reality back then, the internet, electronic commerce, all these high-tech companies created there was a new computational reality, and this created new economic models, results, mathematical techniques. And there was also the other way around. Economic theory, established models sparked new algorithmic models, results, mathematical techniques. And what I'd like to do today is to argue and hopefully also demonstrate that a similar possible connection, two-way connection, could be developed between the classic economic theory of contracts, or maybe also we can algorithmic contracts, and this new object of smart contracts, which to me represents one of the major promises of the new the current computational reality, which is the cryptocurrency systems. So on top of all the contributions to finance, really there is also the potential promise of smart contracts as an object that could influence other computational realities and physical realities. So if you look at the situation today, it very much resembles what was back then in terms of comparing auction theory and auction reality. So if you look at economic contract theory today, so it's mostly irrelevant to the new cryptocurrency reality. And so if you try to see if there is any connection, then most probably you will just say that it's completely separate to different disciplines or objects. But however, I would like to try to claim that this is not the case. And in fact, we could make this theory, we could evolve this theory into a new one, a relevant one, that will have this two-way connection and will enable us to demonstrate how smart contracts can influence many physical realities outside of the finance world. So in order to do that, I'm going to abstract away and describe a general model of contract theory, which will initially look irrelevant. And then I will describe this issue of contractible contracts, which very much resembles smart contracts. And hopefully this will motivate or inspire or whatever. But of course, this is just a very beginning. And so this is just a hypothesis, an argument. So this is a very abstract model, a model of multi-agents and multi-principles. Of course, a contract is this object that is being signed between two parties. One party is called the agent, and the other party is called the principal. And we could even think of contracts that are signed between multiple agents and multiple principals. And so in this very abstract framework, we have agents, and the agents will need to choose a costly action out of a set of possible actions. So each agent has a set of actions to its disposal, and they need to choose one of these actions, and actions could be costly. And then there are the other side, which are the principals, and each principal obtains a gain from the actions of the agents. So the gain of a principal is just a function of the combination of actions of all the agents. And principals may have contradicting gain functions. So some principals want the agents to go left, while others want the agents to go right. This is a model that, for example, was studied by Pratt and Rasteccini in 2003. We could think of many realistic applications of this model. For example, online labor markets, where freelancers complete tasks posted by platforms' customers. So freelancers are the agents, they need to take some actions, and the customers are the ones that are the principals. Online advertising, where a social media influencer, for example, promotes several brands. A marketing agency that bids for ad space on behalf of multiple advertisers. Platforms like Airbnb or Booking.com represent multiple property owners. So all of these are cases where we have one side, which is the principals, try to motivate the other side, which is an agent, to act on their behalf, and the agents represent multiple principals, and the principals interact with multiple agents. So we could also look at it as in an example. Consider the following example. So in this example, the rows and the columns represent the possible actions of two agents. So we have two agents. The row agent, agent 1, has two possible actions, action T for top or B or for bottom. And the column agent also has two possible actions, either left or right. And in this matrix, I describe the utilities that the principals get from the combination of actions of the agents. So note that this is not a usual game as we sometimes see in Game Theory 101, because the numbers inside these cells are not the gains of the agents, they are the gains of other entities. These are the principals. So if agent 1 takes T and agent 2 takes L, then there are two agents, there are two principals. One of the principals, principal 1, will gain 5, and the other principal will gain 0. And so on. So we have 4 possibilities because that's the example. You should also notice that principals have conflicting preferences regarding the agent's actions. So principal 1 prefers TL, principal 2 prefers either BL or TR, and so on. So we have a game here. We can define a game here where in the first phase, every principal announces contracts, which are payments from the principal to the agent based on the action that the agent chose to take. Right? So that's simply a function from the action space of the agents to the real numbers. If you as the principal 1 tells agent 1, so this is like the T sub M sub N, principal M tells agent N, if you are going to take a certain action, I'm going to pay you a certain amount. So that's the first step of the game. The principals announce contracts. Then in the second step of the game, agents observe contracts and decide on their actions. And then we have utilities being realized. The principal's utility is the gain from the combined set of tuple of actions minus the sum of payments. And the agent's utility is the net gain. So it's the sum of payments from all of the principals minus the cost of the action. So this is the agent's utility, which is not present in the picture, but yeah, and it depends on the contracts. So for example, if you go back to this example, then we could see the following possible contracts. Principal 1 could offer 0 for T, for agent 1, 1 for B, 0 for L, for agent 2, 1 for R. So with this contract, principal 1 incentivizes the two agents to play BR. And if principal 2 just does the same, then with these contracts, the agents will indeed, and I'm assuming for simplicity that the costs are 0 of all the actions, just for the simplicity of this example. And so with these two contracts, the agents will indeed play BR, and the gain of every principal will be 3, and the payment of every principal will be 1 to agent 1, 1 to agent 2. And so overall, the principal utility will be 3 minus 1, which is equal 1, I think 1.
So given the contracts,
Yes.
the agent's optimization problems are completely decoupled, right? Like
Yeah. Yeah, exactly.
I'm
Given
an
the
agent,
contracts,
you're an agent, I don't care what you do.
yeah, I don't care. Yeah.
Okay.
Yeah, agent 1 doesn't care about the decision of agent 2.
Okay, so you can think of that as happening simultaneously, independently,
Yes.
given the contract.
Given the contracts.
You have to discuss the timing of the choices of the principals'
Right.
contracts, right?
Yeah, I do have, and in this specific paper, I assume that this is simultaneous. So we have two steps. In the first step, the principals announce simultaneously. In the second step, the agents act simultaneously.
So then does it actually then just become, in your example, two-player game, like just a game in a normal sense?
So there are 4 players here, 2 principals and 2 agents.
Right, but can't I just sort of wrap the agents up into the... So if I think about the strategy space now being contracts.
Yeah.
So I just want to have a game with 2 players, the
Yeah.
principals, strategy space is now the contracts.
Yeah.
Given a choice of contracts, I just fast forward to what the agents will do. I now know my payoff.
But it's not that simple because, so for example, if you think about the action space of the principals, each principal needs to submit a contract which contains 4 numbers. Yeah. And so it's not really just a choice of...
No, but it's a game, right?
It is a game between the principals, and then the agents act upon the incentives that the principals
That's what
create.
I'm saying. So can I think of it actually?
Yeah,
as...
you can, and actually of course that's a very good point. And in fact, if I go back to this credit, so the title of the paper by Pratt and Rastaccini is Games Played Through Agents. So that's exactly what you were aiming at. So it's games that we don't play directly, we play through agents. So I agree with you, but I think it's also a little bit misleading because really it's the principals motivating the agents and it becomes complicated because of that fact. This is exactly the point of this picture, to exactly demonstrate that it's a game played between the principals through the agents. You might notice at this point that these are not very good contracts for the principals, and specifically, each principal can increase her own utility by unilaterally submitting another contract. So, for example, principal 2 may observe that if principal 1 is already motivating the agents to play BR, then there is no reason for principal 2 to also spend money and motivate the agents to do the same. They could deviate to 0, to just offer 0 on all possible actions. And so there are a lot of possible deviations. One deviation is for either principal is to deviate to a contract that offers no payments, free riding on the other principal. Principal 1 can incentivize the agents to, wants to incentivize the agents to play TL. And principal 2 would like to incentivize just one of the agents to move from, for example, agent 2 to move from R to L, and so on. So there could be many possible deviations. And in fact, Pratt and Rastaccini gave a characterization that can be used to show that in this example, there does not exist an equilibrium. So whatever contracts you think of, there will always be a profitable deviation for the other principle. And there does not exist a pure equilibrium in this simple example.
So what were they characterizing? Like what?
They gave a characterization in terms of a linear program, and it's not a very crisp characterization that I could actually describe. So it's a very technical condition.
But if it holds, then what?
I mean, they gave sufficient and necessary conditions for the existence of efficient equilibrium.
Of efficient equilibrium?
Yes, of
Okay.
efficient equilibrium.
Got it.
Yes.
So when you say implied there does not exist a pure, you mean there does not necessarily exist a pure equilibrium?
No, in this example, there does not exist
this
an
example.
equilibrium.
Okay. Got it. So sometimes you'll have one, sometimes you won't.
Yeah.
In this case, you won't.
Yeah, in this specific case, two actions, 5, 0, 0, 4.
And they were characterizing existence of a pure and efficient equilibrium, or just efficient equilibrium.
So they give us a technical tool with which we could check whether there exists a pure equilibrium in this example.
And then one of the clarifying questions, so like this is still, like if you only had one agent, this would still be pretty non-trivial, is that right? Multiple principles, one agent? Like, because it'd still be this non-trivial game theory amongst the
No,
principles.
so if you had just one agent,
Yeah.
then there is even a previous, I mean.
Like one principle, multiple agents seems not that interesting, right?
Right.
But like.
One agent
It
and multiple principles. So I think you could look at it as if it is like an auction. The agent is so I mean each principle wants the agent to take the action that maximizes the gain because there's just one agent. So each principle has So I think you could look at it.
Okay. There's still some game theory left. But
It is some game.
It's definitely simpler than this. Okay.
Yeah, so I'm pretty sure that if there is just one agent, then it's going to be, I mean, equilibrium existence is guaranteed, and I think you could always come up with equilibrium which is efficient, and so
Okay.
I think there's a paper from the 80s that describes that. It's called common agency, one agent and multiple principles. Right. But the whole point of what I want to talk to today is the fact that with multiple agents and multiple principles, there does not exist a pure equilibrium, and this is my starting point. So our idea in this work is to allow more sophisticated contracts. And in particular, we would like to define contracts that depend on other contracts. And these are termed contractible contracts. I could only find 2 previous papers in the literature that actually define or use such an idea in the economic literature. But of course, in reality, we have smart contracts which exactly enable us to do this. But there are other examples. We don't have to only think about smart contracts. For example, if you look at Hilton's webpage, Hilton has a price match guarantee. We always do our best to offer you the lowest price. But if you find a lower qualified price on another site, we'll be happy to match it and give you a 25% off your stay. So if you buy a hotel night with Hilton, you're not exactly sure how much you'll pay. You know what's the best price, the worst price, the highest price that you'll pay, but it's not clear. If you will find a lower price, then you get a lower price. So this is another example of a contract that depends on other contracts. If you could find a better price on Booking.com, then we'll match that price.
So you have to worry about things being well-defined now, right?
Sorry?
You have to worry about things being well-defined.
Yes,
right?
of course. You have to worry about things being well-defined because it could be a recursive definition. Yes, absolutely. But this holds also for smart contracts, you know. Another example, this is from the UK. There are 2 supermarkets, well-known supermarkets in the UK, Aldi and Sainsbury's. Aldi is a lower range prices and Sainsbury's is a higher range prices. And Sainsbury's give a price match guarantee to Aldi. Aldi price match. If you're going to buy a product at Sainsbury, you know an upper bound on how much you'll pay, but if Aldi offers a lower price, they'll match it. So this is the idea that I want to advocate in this presentation to explain how contractible contracts, and specifically a very specific and easy form of a contractible contract, can resolve the inefficiency of the previous game, where there does not exist an equilibrium because of the structure of the game, and turn it into an existence result. And this is exactly the high-level contributions that we saw in the early 2000s regarding auction theory that demonstrated how a theory that on the face of it looked completely irrelevant to the new computational reality somehow turned to be very relevant. And so back then, they used all these abstract models that, even though they were abstract, turned out to inspire actual constructions in the physical world, actual things that happened because of all these theories that interacted. And so that's I hope, would be my conclusion. So I want to explain how to, or to give intuition why I have hope that contractible contracts will be able to resolve the issue that we saw previously in that simple example that we analyzed. And so to do that, I'd like to go back to the world of auctions and to consider this classic setting of simultaneous first price auctions. So this is like, I think, maybe 10 years ago, and Tim had many contributions. In that setting, we have sellers. Each seller is selling an item, and we have bidders. And each bidder is placing a bid on every item, or not on all of them, but on a subset of the items, possibly. And we have many bidders, so the sellers receive many bids, and then they need to allocate the item to one of the bidders. And in the first price auction, they just give it to the bidder with the highest bid. And I want to argue that this is actually very similar to a contract scenario. It's a special case of a contract scenario, because if you notice, the bids are actually payment offers, which is exactly what principals are doing in the contract world. So the entities that are offering payments are the principals. So we could call the payment offer a contract. And then the entities that offer the contracts are the principals. So we could replace this with principals. And the entities that receive the contracts, the payment offers, and act upon that are the agents. And the bidders offer multiple bids, so they value subsets of the items or subsets of the actions of the agents. And so you could actually be more formal and show that this actually translates to be a special case of the previous model that I was just telling you about, where the agents are the sellers, the actions are which principal or which buyer or bidder to give the item to, and the bidders are the principals and the bids are the contracts.
So it's special that the agent cost functions are zero, right?
Yeah, the costs are zero.
Is it otherwise?
Yeah, it is otherwise special because the bidders don't care about actions of agents other than whether I got the item or not. So if I didn't get the item, the bidder doesn't care if the item went to...
So you're saying the principals use contracts where the payment is a function only of that agent's action and not of the full action profile?
Yes, yes, exactly. Yeah. So it is a very special case on one hand. But on the other hand, if you move from first price to second price auctions, then this becomes a completely different story, because now I cannot claim that these bids are contracts, because when a bidder submits a bid to a seller, we have no idea what will be the actual price the price is no longer encoded in the bid. The price is encoded in the bids of the other bidders to the same seller. And so we have here a case where the contract of the bidder to the agent also specifies some dependency to what happened elsewhere. And so this is not a special case of, so the second price auction is not a special case of the previous model. For example, the Pratt & Whitney model. And so the whole purpose the whole technical purpose of this work is to define a different type of contract that will make it a special case, that will make both a first price and second price a special case of the principal agent setting. So that's the motivation. I think, and let me just give you a very high-level highlight of our results. So we define a new type of contracts that depend on other contracts. These contracts significantly expand the set of efficient pure equilibrium outcomes with classic, and in particular, it contains cases where classic contracts do not admit equilibrium outcomes, and the new contracts will admit equilibrium outcomes. And we will also study the price of anarchy of the game because we increase the equilibrium outcomes. And so we have to be careful that we don't introduce very bad outcomes on top of enlarging the set of good outcomes. And so this can be captured by price of anarchy analysis. And we argue that they are still relatively simple. And all these results hold even if each principal is allowed to choose which contract to submit, either a classic contract or the new contract. And so even if the principals have choice, they prefer to go with the new contract. Of course, they could have a much larger choice. They could have many types of contracts, and then the problem becomes even more difficult. But that's exactly my point. The point is that a classic contract theory is so limited in its realm, its assumptions, the way that it is constructed relative to the new computational reality, that if we start studying contract theory with the actual tools that in light of the actual tools that we currently have, then we will be able to demonstrate how these new types of contracts could help not only financial entities, but also Booking.com, Airbnb, Sainsbury's, Hilton, all these physical entities. So recall the game. We have principles that announce, initially it was classic contracts, but I changed the notation from T to B. And so the B, which stands for bids because of my motivation of first price versus second price auctions. So these are, you could think of it as the maximal willingness to pay. Or in the case of a classic contract, this is actually how much they will pay. And then after observing the contracts, the agents simultaneously choose the actions. And then we have the utilities realized, again, as before, gains, which the gain is a function of the combination of actions minus payments. And the agent utility is just the sum of payments, minus the cost, by the way. Just for simplicity, I will, because I'm going to do some very light writing of equations, I don't want to drag the costs with me. But in the paper, we actually do drag the costs all along. Right, and I'm going to change that to what we call VCG contracts, where we don't have these Bs, we have more general payments that depend on the action, but also depend on the other contracts in a very specific way that I will mention soon. The utilities are not the bids, but the payments, and minus with the principals, plus with the agents.
Sort of, motivated by your second price auction example, I could imagine a strong motivation for restricting the dependence on T minus M to be such that your payment to an agent, little n, depends only on others' contracts' payments to agent, little n, and not on the others. So you depend on...
So you're saying in general, this is capital T, but you're saying it will be capital B.
Well, no, I'm saying like...
this is what we will do, actually.
Like in the second price auction one, there's dependence. The dependence is pretty limited. It's kind of like local to each agent, right?
Right. Going back
is that sufficient for your positive results?
Yeah, it is sufficient. I think so. If I understand correctly what you're saying, you're going back to your concern about the well-defined.
Well, that's a separate thing. This is more like a kind of simple versus optimal argument, right? You could imagine that right? Like if I'm an agent and I'm getting paid less than I thought, right? And then and you say, oh, well, that's because these other guys submitted
Right.
these contracts.
Yeah,
It's nice if
exactly.
you only point to the other contracts and how they relate to this agent. Whereas this allows kind of full
Oh,
dependence.
I see.
You see what I'm saying? So like,
Yeah, I see.
you're allowing the transfer to agent 6 to depend on other principals' contracts for agent 9, which is a little weird, right? Potentially.
So yeah, it would only depend on the contracts that the other principals submit to that agent.
So you only need that.
Yeah, I only need that.
That's great.
Yeah. I only need that.
Great.
Yeah, but in general, yeah, okay, I don't want to confuse the others at this point too much. It's just about the payments now will depend on the action, but also on the other contracts. Because I mentioned the word VCG, let me give you a very high-level description of VCG. This is more than enough. It's actually strictly more than enough, but I still want to do it for intuition purposes. In mechanism design in general, our goal is, so there is a mechanism designer, which is like an impartial entity that wants to act for the favor of the society. And the goal of that entity is to choose one alternative out of a set of possible alternatives. So that mechanism designer has to its disposal a set of possible alternatives, and the mechanism designer wants to choose one of these alternatives based on how the players value these alternatives. So we have players, we have many players, and each one of them has a value for each alternative. So player 1 has values, a vector of values for alternatives, player 2 has a vector of values for alternatives, and so on. The way that a mechanism in general works is that the players report their values, all these numbers, to the mechanism designer, and then the mechanism designer chooses an alternative based on their reports, and the mechanism designer can charge payments to incentivize players to reveal their true values. Because this is a game, and once again, the players need not necessarily reveal their true values. And so the output of the mechanism designer is the chosen alternative and the player's payments. So each player pays like a price. Right? And so this is like the general framework of mechanism design. And with VCG, we just have a specific formula for the payments. And we know that this formula causes the payments to declare the true, or incentivizes the players to declare their true values if what the mechanism designer does is to choose the alternative that maximizes the sum of values of the players. So if the mechanism designer sums up the values of alternative A, the values of alternative B, and so on, and chooses the alternative that maximizes the sum of values, then the VCG payment formula incentivizes the agents to declare the true values. So this is VCG, this is mechanism design. You only don't know the formula, but you don't really need to know it. But in any case, I'll say it in the next in a few minutes. And intuitively, only in terms of motivation, we are inspired by this framework, viewing the mechanism designer as the agent. The alternatives that the agent has is the actions that the agent has. And the players are the principals. And the principals have values for actions. And so the principals submit values for actions to the agent chooses an action, and then gives an output. I'm sorry, that's the output, the action, and that's that. But of course, notice that this is a very, very shaky motivation, and there is really no formal connection to VCG, and this motivation is probably even flawed because of several reasons. For the first reason is that the agent is not a mechanism designer, it's not an impartial entity. The agent is a strategic player that wants to maximize their own payoff rather than to maximize the principal's sum of values. So that's the first difference. The second difference is that the principals, it's not only just one agent. There are multiple agents, and the principals pay all of them. And so it's not just a single mechanism designer, there are a lot of agents. So that's the second reason. And the third reason is that when I say true values, what do I even mean? There are no true values, because in the mechanism design framework, we have values for alternatives, But if I view alternatives as actions, and we have multiple agents, then what's the value of the action T? I don't know, it depends on what the other agent will do. And so truthfulness is meaningless. There are no values for actions. So it's really a very flawed comparison, but intuitively it helped us to formalize some solution, which I don't even know if that's the optimal solution. But at least that's like one step forward. Right, so that's the intuition for the VCG contracts. And now, given this intuition, I'd like to define exactly the VCG contracts. So a classic contract, again, is this function that gives a number to every action. And you could think of it as the principal's maximal willingness to pay for that action. And then we have a specific function which depends on the classic contracts and also depends on the actions of the agents. This function determines the payment of principal M to agent N. And VCG contract will be a specific form for this function T. And we had the intuition from before. The agents are viewed as the mechanism designers, and the principals are the players, and the B's are like their valuations, whatever this will be. And the principals pay the agent the VCG payments. Right? So because of this third bullet, we could attempt and write what is the VCG payment. So we could define the actual function T to be the VCG payment, like taking the VCG formula and trying to see if that will work here. And so so the VCG formula has a very catchy textual explanation, verbal explanation. Each principal pays to the agent the damage that the principal causes the other principals. And that damage is more formally defined to be the difference between two terms. The first term is the aggregate value of all the other principals from a given action that the agent does. That's the first term. And the second term is the value of all the other principals from the action that the agent actually takes. So the first thing is the maximal possible value for the others. And the second term is the actual value of the others. So the difference between the maximal possible and the actual to the others, that's the damage that the existence of this principle caused the others. So that's the difference. So that's the formula. And as you could expect, actually this doesn't work. There's no reason for it to work. It's not a VCG. There's no connection to VCG. So this is really funny, but it doesn't work. But luckily, something very similar did work. So instead of this VCG formula, the thing that did work is a very related formula where the first term remained the same. The second term was amended so that we add, so it's no longer only sum over all the other principles, where we also added the bids of this principle, and we again maximized over all possible actions. And then we added to the payment, we added the bid of that principal to that agent for the chosen action. So this is like a formula that is related to the VCG payment. It's not the VCG payment.
If A equals AN, they're the same.
Exactly. So I have two types of intuition to offer you. The first one is a short one, so I will. That's exactly what you just said. Let me repeat it. And so the second formula becomes equal to the first formula in one specific case, in the case where the maximum among all the A's here is exactly equal to the action that the agent takes. If the action that the agent takes maximizes the possible sum of actions, sum of bids for that action, then this maximum A becomes AN, and this cancels out because there's a minus sign here. And so this cancels out, and everything that we did goes back to the VCG payment. Right. In other cases, it does not. So it's not always the VCG payment, it is only the VCG payment in a specific case, but this will turn out to be the case that happens. And to explain that, I will skip to the second slide. So I'm a little bit, I can't do it more slower than I already tried to do because we have this time limitation, but I'm happy to answer questions later on.
And so
right.
this is done completely separately, agent by agent, right?
This is done per agent, right? But this is also like the general definitions. So we defined it as BN here. So it's only the bids of that this agent N got. Yeah, so this is like, this connects all your previous questions as well, Right, so that's the payment formula. If I look forward at what the agent will do, given a set of contracts, initially it could seem unclear what action will the agent take. Remember that in classic contracts, it's very simple. The agent will simply look at the action that maximizes the sum of bids from all the principals. Because what the agent will get is simply the sum of bids from all the agents, from all the principals. And so in classic contracts, the agent chooses an action that maximizes the sum of bids. So this is exactly, in classic contracts, the agent exactly chooses the action that maximizes this. What will be the action that the agent will choose in VCG contracts? So the agent will simply choose the action that maximizes the sum of payments. It's no longer the bids, it's the payments. And but if we write the formula for the payments, so I just did copy-paste, we could see that the first two terms are constant because this is maximum over all actions, so it doesn't depend on the specific action that the agent takes. The second term, again, doesn't depend on the action that the agent takes, so it's a constant. So it only depends on the bid, even though the actual payment will not be just the bid, it will be the bid plus minus something. And so this is like going to be a constant plus the sum of bids. And so it's going to be exactly like in the classic contract. Both in the classic contract and in the VCG contract, the agents are going to look at the bids and are going to choose the action that maximizes for them the sum of bids. If we go back to the formula, the agents are going to choose the action that maximizes the sum of bids. So AN will be this A that maximizes this. And therefore, as Tim said, this cancels out, and we go back to the VCG payment. Right, so these are the VCG contracts. I hope I managed to give you a little bit of intuition how they work. And so the VCG contracts don't change agents' incentives. They will still look only at the bids and will choose the action that maximizes sum of bids. It does change the incentives of the principals. They will generally pay less because the maximum over here is larger than the maximum over here. And so if you interpret this as the maximal willingness to pay, they will actually, in general, pay less. And let me again tell you about our results without any technical details. So the first result says that every pure equilibrium with classic contracts will also be an equilibrium with VCG contracts. So if we have a tuple of contracts, of bids, that are equilibrium for classic contracts, it will be also equilibrium with VCG contracts. But there exist cases in which no equilibrium exists for classic contracts, but there is an equilibrium with VCG contracts. And these are not just a rarity. The measure of such cases, which by cases I just mean gain functions, in the space of all gain functions, the measure is positive, but we don't really know how much is the measure. We don't know if it's 50% or 10% or whatever. But
do you know if it's 100%?
No, it's not 100%. That's for sure. Yeah, unfortunately. Yeah.
Just so I understand the first statement.
Yes.
So you're saying, like, if you take a pure equilibrium with classic contracts, you keep the contracts exactly the same, but now you let people deviate if they want to any of your very rich space of
Yes.
contracts, not necessarily
No.
just VCG contracts.
No. You keep the space of contracts to be VCG. They only deviate by submitting different bids. So the space of so in this result, the space of contracts is just VCG contracts. So the actions of the principals is just to submit different bids, but
I wouldn't even call that a space.
Translation of bids to payments depends on this framework.
Okay, but there aren't any even.
But if you allow them to also...
No, okay, now I'm confused. So
Yeah.
as a VCG contract, you could mean two things. You could mean I allow TMN functions of that general form, or you could mean that specific payment function at the bottom.
This is enforced.
Huh?
In what we analyze, this is enforced. So the game only gives them freedom in submitting the classic. So a VCG contract has the classic contract and the payment function. And this is a payment in the analysis, we assume that this will be the payment based on the contracts submitted, the bids submitted. And that's a good question. I completely agree with you that this should be generalized. We did one step forward and we increased this space to also include the payment function, which is just the identity. So the function will be just the classic contract. And so they won't deviate to that as well. But of course, and if you have smart contracts in mind, then they are of course unlimited. And so it's not clear, probably even not correct, that that will be an equilibrium anymore, VCG contracts. And I don't know what will happen. So that's an excellent question. Yeah. But we did enlarge, so with classic contracts, I mean, if you have, so this is exactly what I mean. If you have smart contracts fixed already in your head, then you don't even accept this notion of a classic contract. Why are the principals limited to submit just smart contracts that do not condition on any external events? Doesn't make any sense, right? So we make a very small step forward to increase the space a little bit and analyze what happens in a specific way, of course, so that the improvement will be clear. Right, so back to your question, so it's equilibrium with classic contracts is an equilibrium if we change the payment function from classic contracts to VCG contracts. It is also an equilibrium, I will have it later, but maybe I should say it right now, that it's also an equilibrium if there is a step zero, each principal can decide for themselves whether they want to use classic contracts or VCG contracts. They will always use VCG contracts.
So I mean, intuitively, is it like basically everything stays the same except you might get an additional rebate as the principal if you switch to VCG?
No, not everything stays the same. So let me answer your question after I describe this picture. So in the blue picture, there are every like virtual dot on this space, on this large black space, is a tuple of gain functions. In the blue circle, the smallest circle, these are all the tuples of gain functions, games, for which there exists an efficient equilibrium. Just replace SP with equilibrium. I missed that. Efficient equilibrium when you have classic contracts. In the green circle, you have, these are all the gain functions where you have efficient equilibrium with VCG contracts. And there could be other cases as well.
So I guess, just inside the blue circle, it was back to that first result again, where you're just saying every equilibrium, I mean, your proof actually says like, take something in the blue.
Yes.
Keep the contracts exactly the same, switch the payments, your VCG payments, and it stays in equilibrium, right?
Yeah, it stays in
equilibrium. There's a stronger statement.
It's
not just that you still have
not
existence.
for everything, but for a larger class of
No, I'm just working
functions.
in the blue. I'm only working in the blue here, right? So I'm just inside the blue.
Yeah.
So it's your argument that the blue is inside the green.
So the argument in
right?
the blue says, everything stays,
So I was asking, is the intuition basically that just like from the principal's perspective, if you switch, it's just like you're paying, you get some rebate. So you said, because you also said you always prefer VCG to classic.
That's a good question.
Right? So my guess is like the way the proof goes is you're like, look, if you switch from classical to VCG, you're just going to get a rebate compared to where you were before.
No, I actually think that there will be no rebate. It's going to be exactly the same. I think it's just going to be exactly the same.
So it is just completely strategic.
Yeah, I think that if there is...
Including for deviations. So you need to show two, right? So you're verifying equilibrium.
I'm not
Okay,
sure.
let's talk
I have to
offline.
think
We
about
can
it
talk
later.
offline.
Yeah, I'm not sure. But let me also say the other two results. So we have increased the number of equilibria. Even inside the blue circle, there could be other equilibria. So we could increase the price of anarchy even significantly, but we showed that that's not the case. We couldn't exactly pinpoint the price of anarchy, and of course, it was not studied for classic economic contracts, and so they don't even know what is the worst case. They only think about the best case. So it turns out that the price of anarchy for both of the contracts is about the number of principles, either that or +1. So it doesn't decrease in the worst case. Yeah, and I already said the last bullet that if you have pure equilibrium with VCG contracts, it's also an equilibrium in an expanded game where the principals can decide whether they want VCG contract or classic contract. So let me just summarize. So we study a new type of contracts, termed VCG contracts, where payments depend on bids submitted in other contracts as well as on a principal's own maximal willingness to pay. This has been termed contractible contracts by two other papers, Peters and Sentence. That's the only two papers that I know in the literature, and since this paper is already published, I assume that these are indeed the only two papers that have this idea of contractible contracts. If compared to the reality, where we know that contractible contracts are being used, and then that's a huge discrepancy. Right, so that's in terms of the motivation. We show, in terms of results, we show that the VCG contract expand the set of efficient equilibria in a meaningful way. Even if principals are allowed to choose between classic and VCG contracts, the additional equilibria do not increase the worst case price of anarchy. I also have a follow-up paper, again with Elisheva and with Inbal and her student Tal Alon, and that paper studies VCG contracts for a common agency setting with moral hazard. So in the newer setting, the principals cannot observe the agent's actions, they only observe the outcomes, and they have to infer the actions for the outcomes. So that's more complicated, and the results are more complicated. And of course, we have many future directions. For example, as already discussed, other types of useful contractible contracts, better price of anarchy, wider equilibrium existence, for other types, not for VCG contracts. And maybe also actually thinking about how to implement contracts from contract theory using smart contracts. There are issues that are not dealt with, like the complexity of different types of contracts, the cost of different types of contract, and so on. And that's that.
I guess at a high level, so you said like the principals, they do it simultaneously, right? Like they release, so like, do you see extensions to like, because like if you do smart contracts, it's not going to be simultaneous.
Right.
So like what would change and like, just in general, like has that been analyzed for classic contracts?
That's a great question. By simultaneously, I don't mean that they look on their clocks and step a step forward exactly the same time, but they determine their contract without knowing what the other principals determine. Sometimes this is correct, sometimes this is not correct, I agree. But it's not necessarily incorrect in smart contracts because if there's a deadline and we need to submit something and we submit it very close to the deadline after working on it for a week, then it's the assumption of simultaneously approximates reality. Sometimes I agree with you that the assumption of simultaneity doesn't agree with reality. I have this is called online algorithms, of course, and I have some results on myself, but it makes everything very much more complicated. So, I mean, for me, I think this is like a simplification that I'm willing to take right now because there are other issues that I feel are more important. But that's always a situation that is worth an attention at some point.
In the blockchain context, we often talk about enforcing that through cryptography, right? Where you you sort of commit to obfuscated version of
Thank
your
you.
contract, and then you reveal it only after both people have
Yeah.
committed. And there's other issues that come up, but like that's one way to
Right. Thank you. Thanks.
get your information assumption. Yeah.
Thanks.
Okay, one more quick thing.
Yeah.
So like usually here you said like, I guess for every agent it's basically independent, right? Like once you
Right.
see the bids,
Yes.
like what the principal sort of bid for other agents is independent in some
Yes.
sense. So I was wondering like, are there scenarios where that's not true? Like let's say the principal sort of only gets a gain when it gets 10 agents to do what it wants them to do. Just curious in general. like if that's something
I mean, I
that's-
could imagine situations where if multiple agents, where actions could interfere with one another. So, for example, the agents could care about the actions of the other agents because there's interference. Yeah. Yeah, I mean, if you look at what happened in the early 2000s and the volume of new models that were inspired by actual difficulties in reality, trying to align reality and theory. So I think something similar should happen also with contract theory.
Yeah, I guess more broadly, sort of computer scientists found out about mechanism design like 20 years ago, and then all of a sudden there was an explosion of work.
Right.
And even though they're equally classic, for some reason computer scientists only found out about contract theory like a few years ago.
Right.
So we're like 3 years into what will be possibly 20 years.
Exactly.
Yeah, I agree.
Yeah.
Yeah. All right,
No,
let's-
and even more than that, what I argue is that in contrast to what happened with mechanism design auctions, where computer scientists learned about the model, but then discarded all previous results started from the 70s, and then gradually built their own way up. What we see now, and this is like a word of criticism, what we see now in computer science is that we adopt the classic model as like a holy grail and just study computational issues. You know, how much is it complicated to calculate a best response in the classic model, or
Interesting.
something like that.
So you think
And
computer
that's-
scientists have grown too deferential of economists in the last 20 years?
To the
respectful?
opposite of differential.
Okay.
To respectful, or too close.
So we got to get back to like,
to that
let's
spiteful
do it all our own way.
situation.
Okay, cool.
I mean, there's contract theory. It's cool, but we could.
Let's make it our own, you're saying.
Yeah, we could make it our own. Yeah,
Cool.
exactly.
Cool.
Thank you.